Okay, hi everyone. Welcome to the 11th lecture of data mining and machine learning. And today we'll focus on Gaussian mixture models. So the Gaussian mixture models are a very common unsupervised learning model and learning technique. And the motivation of Gaussian mixture models is the following. So we've had this before, that the ubiquitous assumption in statistics and machine learning is that our data has been produced by some unknown probability distribution P star out there. And Gaussian mixture models fall into the paradigm of density estimation, where the goal is we want to retrieve P star from our training data. So P star is unknown and we want to essentially go back to P star and estimate this density from our samples, and then use this for useful insights about the data. And the simple yet powerful model are these Gaussian mixture models, or GMMs in short. And the idea is pretty simple. They combine k Gaussian components into a single density model, as we'll discuss. So I assume you're familiar with Gaussian distributions from basic statistics courses, and GMMs essentially combine many of these components into a complex density model. And we'll discuss the canonical learning algorithm, the expectation maximization algorithm, which can be understood as essentially a soft or probabilistic version of k-means clustering, which we had before. So the outline for this lecture is the following. So we'll have 4 sections. In the first section, we'll give a recap about random variables and probability densities, probability distributions and densities. And in particular, we'll discuss Gaussian distributions in section 2. So Gaussian distributions over one random variable, and we'll discuss how to do maximum likelihood learning in them. And then we'll go to many random variables and generalize Gaussians to multivariate Gaussians. And then in section 4, we'll discuss Gaussian mixture models, which essentially take a lot of Gaussian components and combine them into a flexible density estimator. Let's start with our discussion of random variables and probability densities. So we'll introduce the notion of a random variable or a random quantity, which essentially represents our data. And we'll discuss what a probabilistic event is. And then we'll discuss probability distributions, which assign probabilities to events. And probability distributions are somewhat hard to work with in practice, and therefore we'll introduce an easier representation, a so-called probability density function. And first, here's a little disclaimer. So our treatment of random variables is somewhat simplified here. So we'll treat random variables, as the name says, as random variables or random quantities. So in rigorous probability theory, the story is somewhat more complicated. So actually, there are some preliminaries and technicalities. So actually, in rigorous probability theory, we have the notion of a probability space, and the random variable is really a function from this probability space to a certain state space. So we will omit these technicalities. So what we'll discuss here is not really wrong, but essentially it omits some mathematical details here. And so if you want to catch up on this, I can really recommend you this book by Jeff Rosenthal, First Look at Rigorous Probability Theory. So this is, of course, not subject to test. So this doesn't come to test. This is actually just a reading recommendation. So I said, so our treatment of random variables will be correct, but a simplified version, essentially. So what is a random variable? So, and again, so we'll have an intuitive notion of random variables. So it's a variable which assumes random values or a random quantity. And essentially our data is, all our data items are essentially draws from random variables, so to speak. And so they can take values in a certain range. For example, they can be binary when they assume values 0, 1, or they can take rather strange states like ice cream, chocolate, and gummy bear. So this is also good. So like this would be a categorical random variable. Or a random variable can be real if it assumes real numbers as states, or it can assume natural numbers as states. So for example, a typical binary variable would be a coin flip or a so-called Bernoulli variable. And or the outcome of a dice roll is often represented as a categorical variable. So like each outcome of the dice roll is a different category. Or we can look at the height of a random Dutch person. This would be a continuous positive real valued variable, so continuous real valued. Or we might consider the number of meteorites hitting Earth each year. So this would be so this would assume natural numbers. So the number of meteorites is a natural number. And this is often modeled with a Poisson variable. And essentially any data you work with in statistics and machine learning is actually a random variable. It stems from a random variable. So for some notation, we denote random variables with uppercase letters. So X, Y, and Z, for example. And their state spaces we denote with these calligraphic letters. So calligraphic X, calligraphic Y, calligraphic Z. So for example, if calligraphic X would be R, the real numbers, then X would be a real valued random variable. Or if calligraphic Y is the integers, then Y would be an integer valued random variable. And if calligraphic Z is a 0, 1, the set containing 0 and 1, then Z would be a binary random variable. So calligraphic, uppercase letters are random variables. The calligraphic uppercase letters are the state spaces, so the set of the values a random variable can assume. And so elements or states, so generic states are denoted with lowercase letters X, Y, and Z. So X, Y, and Z would be elements from the state space. So for example, if X is R, then X would be just a real number. And we talk about generic states, so we don't say a specific real number, but we symbolize them with these lowercase letters. So X, Y, and Z uppercase random variables, the calligraphic uppercase variables, they're state spaces, and states are referred with the lowercase letters. Okay, so in probability we talk about events. So what is an event? So consider a random variable X with a certain state space, calligraphic X. And an event is actually really simple, a simple thing in probability. Namely, an event is just a subset of the state space. So a subset A, subset of the state space is called an event. And essentially this can be interpreted as the event that the random variable assumes a value out of this set A. So A is this event, and you can figure this that, so X is the whole state space and A is just a subset of the state space. So X assumes a value in the state space, and A essentially is like a bin, which where the random variable might fall into or not. And if the random variable falls into the bin, we say that this event has happened. So this is a bit abstract, and we'll have an example on the following slide. But for some more notation, so if we have two events, which are just subsets of the state space, A and A prime. So if A and A prime are both events, and if it happens that they are non-overlapping, so the intersection is the empty set, then we call A and A prime disjoint or mutually exclusive. And in particular, we define the so-called complementary event. So if A is an event, and if we take the complement A bar, so which is just the complement with respect to the state space. So all the x's from the state space which are not in A, so this is the complementary event. And of course the A and A bar are mutually exclusive. So here are, for an example, consider a random variable X which represents the outcome of a dice roll. So the state space of X would be 1, 2, 3, 4, 5, 6. So all possible outcomes of the dice roll. And now here are some events we might be or also might not be interested in. For example, we might be interested in whether the outcome of the dice roll is a prime number. And if we just pick all the prime numbers from the state space, this would be 2, 3, and 5. So this set containing all the prime numbers would represent the event. The outcome is a prime number. So this essentially shows that the subsets of the state space can actually represent interesting events, or potentially, if we are interested in prime numbers, then this might be an interesting event. Or Fibonacci numbers would be 1, 2, 3, 5. And so the outcome would be a Fibonacci number is represented with this set. Or same, if we're interested in odd numbers, then we consider the event containing 1, 3, and 5. Or even would be 2, 4, 6, and so on and so forth. So larger equal 5, 5 and 6, smaller than 5, 1, 2, 3, 4. So we see that actually we have like this interesting or potentially interesting abstract events: odd, even, Fibonacci number, prime number, smaller than 5, larger equal 5. And all of them are just represented with subsets of the state space. Note, so these two events here are mutually exclusive, and they're also complementary events. And same here, odd and even are complementary events, and therefore also mutually exclusive. So how does this work? So say we roll now our dice, and the outcome is now 2. Then essentially the bell rings, and essentially 4 events have happened simultaneously. Namely, the outcome is a prime number and a Fibonacci number, and it's even, and it's smaller than 5. So events can of course happen simultaneously, except if they are mutually exclusive. Then only, so if we have 2 mutually exclusive events, then only one can happen. But of course, many events can happen at the same time. Or we might roll the dice a second time. So we roll it, and the outcome is now 4. And now the event that it's an even number and that it's smaller than 5 have happened, and the other events have not happened. So 4 is neither a prime number, nor it's odd, nor it's larger than 5, and it's also not a Fibonacci number. Or the outcome might be 3, and then essentially these 4 events, these green events here, have happened. So events, just subsets of the state space, and essentially any event we might be interested in can be represented with a subset of the state space. So therefore, the subsets of the state space are called events. Now we're talking about probability, and therefore we'll have a probability distribution. So what is this? So let's again consider x, which is a random variable, and it takes values in a state space calligraphic x. And we just defined what events are. They are just subsets of x. And so a probability distribution, denoted as p underscore x, so the probability distribution of x assigns a real number between 0 and 1 to events, so to the events we are interested in. And so this number between 0 and 1 is called the probability. So the probability distribution assigns a probability to events. So it's, well, this is what a probability distribution does. And it does so by while obeying certain rules. And the rules are essentially these here. So the probability distribution must assign a 0 probability to the empty set. So this is the empty set. It must assign 0 probability to the empty set. And it must assign probability 1 to the full set, to the full state space. And it must do the following. If we have an event A and we have the probability of A, then the probability, so this must be given as 1 minus the probability which is assigned to the complementary event. So probabilities of complementary events must be given, must obey this this equation. So in particular, probability of A plus probability of A bar must give 1. And essentially this is just a special case of the following rule. So if we have multiple events, A1, A2, A3, and so forth. So, and if these events are disjoint, so they are all non-overlapping, then the following rule must hold in probability distributions. So we have these disjoint events, and if we just summarize, if we combine them into a big event by taking the union of all these events, so if we take the union of these disjoint events, then the probability of the union event must be given as the sum of the individual probabilities assigned to the individual events. So this must always happen for disjoint events. So if the events are not disjoint, so if they are overlapping, this does not necessarily hold. For disjoint events, this must always hold. So this is actually just the formal definition of a probability distribution. So it takes events and assigns a number between 0 and 1, and this is the probability. It assigns a probability to these events. And essentially it just has to obey these rules. So this is a formal description of what a probability distribution is. So, but what is probability now? So how do we interpret this? And so as said, this is actually just a formal definition, and there are several definitions which you can actually apply here. And the classical interpretation is the so-called frequentist interpretation. So classically, probabilities stem from this interpretation, and the frequentist interpretation is that the probability of A is essentially the relative frequency that X falls into A. So essentially, this means that we must draw realizations of X, and we must, in principle, be able to do infinitely many repetitions. So we draw infinitely many results from this random variable X, and then we count how often does it fall into A. So essentially, you can figure A as a bin where the random variable falls in or not. So, and if we have now a certain number of trials, we just count how often does the random variable end up in this bin, and then we divide by the number of trials, and then we let go the number of trials towards infinity. So this is essentially the relative frequency. How often does X fall into bin A, so into event A? And this is set, so this is the relative frequency, and therefore the frequentist interpretation of probability. And yeah, I said this is the classical definition of probability, but not the only one. And so the most prominent other interpretation is the Bayesian interpretation, where essentially the probability is interpreted as a belief or a truth value. And essentially you can see this as a relaxation of binary logic. So in binary logic, we have true and false. And so true and false, 1 and 0. And essentially probability now relaxes this to soft values or continuous values between 1 and 0. So essentially grayscale truth values, a relaxation of binary logic. And in particular, so if you consider the statement, tomorrow the sun will shine, then you have actually a philosophical difficulty to actually define a frequency, because there's really only one tomorrow. So you can actually not collect infinitely realizations of tomorrow the sun will shine or not. And so therefore this Bayesian interpretation has sometimes advantages over the frequentist interpretation. So both interpretations are fine, and for the sake of this lecture, it doesn't really matter. So like you pick whatever you want. So if you're happy with the frequentist interpretation, that's good. Then just think about probabilities as relative frequencies. And if you are more a Bayesian person, then you can think about this as a relaxation of truth values. Okay, great. So this is the probability distribution, or also called sometimes probability measure. So these probability distributions, all they do is assign probabilities to events, which are subsets of the state space. And therefore, probability distributions are actually functions which take whole sets as arguments, so these A's, and return numbers. And this is typically hard to work with and to represent on a computer. And in order to make our life easier, we will use representations of our probability distribution using probability distribution functions. In particular, for discrete random variables, there's the so-called probability mass function. And for continuous variables, there's the so-called probability density function. In this lecture, we will only consider continuous random variables and therefore only probability density functions. So what is a probability density function? So let X be, again, a random variable, and now we assume it has a state space, the real numbers. So the state space of X is the real numbers. And now if it happens that there exists a function p of x, which maps real numbers to positive real numbers, potentially also infinity, so it maps the state space of X to positive real numbers. And if the following happens, if we take this function and we integrate it over an event over set A, so if we take the area under the curve of this function based on the set A, if this always happens that this is the probability of A, then we call this a probability density function. So we call this then in this case we call Px a probability density function, or PDF of X, or also short probability density, or also just density. And we define if a random variable with state space R has a density Px, then we call this random variable a continuous random variable. So this is maybe a bit formal, so let's look at an example. So here we have, well, the state space of X, so this is just a real line. And here we have our probability density. So say this would be the probability density of our random variable. Then the following happens if we consider any event. So any event A, for example, this interval, so this purple interval, which is a subset of the real line. If it happens that the area under the curve, so the integral over this set A, so the area under the curve based on this set A, if this blue area is the probability of A, and if this happens for all events A, then this is our density. So for example, it must also hold for this event, so which is actually a union of three intervals. So this small interval, union with this medium interval, and union with this long interval. And we again integrate the density over this set. So we take the area under the curve based on this A. This must be the probability of A. Also, we might also consider an event going from -infinity to a certain threshold. And so we consider this very long interval, and again we integrate the density over this long interval, and this blue area must be the probability of this set. So it must hold for all events we consider that the integral, so the area under the curve, based on this set A, must be the probability of A. So this is what probability density is really. Yeah, so some notes. It always holds for probability density that it's non-negative and it must integrate to 1. So if we integrate over the whole real line, then we must get 1, because the integral over the whole real line must be the probability of the real line, and that by definition of probability, this must be 1. So it's just a function which is non-negative and integrates to 1. And conversely, if we have a function which is non-negative and integrates to 1, then we can guarantee that this is always the PDF for some random variable x. So there's an intimate connection between continuous random variables and these kind of functions. So a PDF is just a function which is non-negative and integrates to 1. And so it goes both ways. So all PDFs have these properties, and all functions which have this property are a PDF for some random variable. So a slight warning here. So probability density is not equal probability. So probability only comes back if we integrate the density. So only the area under the curve is the probability. The density itself is more like a rate of probabilities. So it's not probability itself. So only when you integrate density, you get probability. Okay, great. So this already summarizes this first section. So we introduced random variables, so random quantities denoted with uppercase letters, and their state spaces are denoted with these calligraphic letters. In this lecture, we'll actually focus on real-valued random variables, so these state spaces will be typically the real numbers. And later, when we discuss multivariate random variables, also Euclidean spaces. So for example, the three-dimensional Euclidean space for three-dimensional random variable. The states are denoted, so generic states are called denoted with lowercase letters. And yeah, we defined the probability distribution, which just assigns a probability to events. And we said events are actually just, well, subsets of the state space. And we defined the probability density, which gives you the probability of an set A if you integrate it over the set A. So area under the curve based on the set A must deliver the probability. If such a function exists, we call it the density. And yeah, random variables which have a density are called continuous. And we also shortly discussed this frequentist and Bayesian notion of probability.